So we'll do 1d, the factors, all factors of 243. So let me give you a second. Use your calculator. Start by finding the limit, right? The square root of 243, whatever that is. So you start there. It's 15 something, isn't it? So 15 will be the last one you need to look at. That'll be our limit. Start with 1. Just divide by 2, divide by 3, divide by 4, all the way through. 2 doesn't work. 3, whatever that is, 81. 4 doesn't work. 5, 6 doesn't work. 7, 8, 9. That's it. There can't be any more. Are you still going? 10, 11, 12, 13, 14, 15? Well, I guess you go to 15. Yeah, nothing else is going to work. How do I know that? How do I know that right away it's just going to be 1, 3, and 9? Nothing else. Because I'm looking at that 243, and I'm looking right here at 3 times 81. So I'm thinking about the breakdown of that 243. 81 is what? 9 times 9. And each of those 9s is what? 2 3s. So what's really in a 243? Bunch of 3s and nothing else. See what I mean? So what? What does that mean? Well, that means no other numbers that don't... Any number that has something other than 3 is not going to go into 243. 243 is only made out of 3s. So I don't need to bother trying 10. No way. 10's made out of 2 times 5. He's got a 2 in him and a 5 in him. How could he go into 243? How could he be a part of 243 when 243 is only made out of 3s? See what I mean? See how primes give you powerful, quick insight into numbers? Even here. You don't have to do that, but it'll save you a lot of time. If you think about primes all the time, it really makes things quicker and easier. So I know, it's just going to be 1, 3, 9. Things that have 3s in them, right? Not anything that has other numbers. So what's the next number with a 3 in it? It would be times 3, 27, and we've already got that over there, so we're done. That's how I knew we were done. The next one, another times 3, right? I'm just going times 3, times 3, times 3. 27, already got it, done. Anyway, you don't have to do that. You can just use calculator. But just letting you know, primes are the quick way to understand numbers. So there we go. So our answer to this question then would be 1, 3, 9, 27, 81, 243. Those are all the numbers that go evenly into 243. Good? Easy enough? Questions on doing primes? I'm doing factors. It says find the smallest counting number, this means regular number, that has the following number of divisors. That's kind of a funny question, huh? Like, do you understand what they mean first off? Let's make sense of what they even mean. Like, what's the small? Let's just start with the 6 here. I'll just jump down to the 6. What's the smallest number you know that has 6 divisors? 6 things that go into it. If I was you, I'd be thinking, I don't even know one number that has 6 divisors. What do you mean? How do you come up with a number that has 6 divisors? 6 numbers that go into it. Let's just take a number, for example. How about 10? How many divisors does 10 have? How many things go evenly into 10? 4. How'd you know that so quick?
1, 10, 2, 5.
Good. 1 times 10, 2 times 5, right? So 4 things go into 10, right? He's got 4 divisors. So he'd be in this category, huh? He'd be a number with 4 divisors. So what's a number that has 6 divisors? 12? I was thinking 12 also. I think so, huh? 1 times 12, 2 times 6, 3 times 4, and then they would repeat after that, huh? Yeah, so that has 6 of it. Yeah, so 12. But is it the smallest? Probably. But it's for sure one number that has 6 divisors, right? But is it the smallest number with 6 divisors? Probably. How do you really find that out? It's kind of a weird question, huh? Isn't that weird? Like, how do you find out how many divisors a number has? And you're all thinking, I don't know, Mr. Heron, tell us. There's actually a weird rule. Let me, I wish we had time to derive it all, but we don't. So let me just give you the game plan. Basically, if you take a number and you break it, here's what, I'll show you with the 12 and then I'll give you the general rule. If you broke down the 12 into primes, it's all about primes, everything's about primes. You go 3 times 4 and the 4 breaks down 2 times 2. So 12 is really made out of 2 squared times 3, isn't it? 2 squared times 3. So what that means is all the little numbers, like all these numbers, that go into 12 are really different combinations of some 2's and some 3's. Are you tracking with me so far? So anything, if you're saying, I want to make a number that is part of 12, basically, that goes into 12, it's a piece of 12. Well, if you're going to make a number that's a piece of 12, you got to make it out of the building blocks that make the 12. And what's 12 made out of? 2 2's and a 3. That's what he's made out of. Okay, so you mean like all these guys are just made out of 2's and 3's? Yes, they are. Yes, they are. Like look at 4. 2 times 2. He's made out of the 2 2's. Look at 6. 2 times 3. He's made out of one of the 2's and one of the 3's. What about the 12? That's made out of everything, right? 2 2's and a 3. The 3 is just a 3. The 2 is just a 2. Now, what about the 1? He's made out of no 2's and no 3's. I know that might seem like we're cheating or something, but basically 1 goes into every number, huh? 1 goes into every number. So, well then, how do you know there's going to be 6 of them? Let me ask you this question. What if I said, hey, I've got, what's a good way to do this? I've got 2 A's and a B. And what are all the different things that you can make using some of the A's and some of the B's? You don't have to use all the A's, you don't have to use all the B's. What are all the different combinations of things you could do? You know what you could do is you could put it in an array. You could say, I'm going to use no A's, 1 A, or 2 A's. I'm going to use no B's or 1 B. And then you could just say, all of those are going to be combinations of some A's and some B's. How you doing? Am I losing you completely? So that's making sense. So what I'm saying is, what if I said, I want to know all the ways of making combinations of A's and B's. Probably I shouldn't do the A. I'm probably confused with A and B. Let me just go back to the 12. What is the 12? 2 squared. Ooh, I'm erasing it. 2 squared times 3. So that's what I'm really doing. So 12, which is 2 squared times 3. What that means is if you want to make stuff out of the building blocks of a 12, you can use no 2's, 1 2, or 2 2's. So no 2's is just the number 1, 2, and 4. No 3's, which is 1, and 1 3, which is 3. Let me hold up there. Why would I say no 2's is that 1? Well, because if you have no 2's, you have nothing. But you have the number 1, because 1 goes into every number. And if you have no 3's, that's really the number 1, because 1 goes into every number. So I'm saying, basically, if you wanted to make stuff out of the building blocks of 2's and 3's, you could use, you say, I'm going to build something, I'm going to make it out of the pieces, the building blocks of a 12, the 2's and the 3's. You can use no 2's, 1 2 or 2 2's, no 3's or 1 3, right? And then any combination thereof will make a divisor. 1 times 1 is 1, 1 times 2 is 2, 1 times 4 is 4, 3 times 1 is 3, 3 times 2 is 6, 3 times 4 is 12. There they are. There's the 6 divisors of 12. Do you see that? Those are all the numbers that are going in there. Am I like totally doing the Charlie Brown teacher voice right now? The wah, wah, wah. Nothing's coming across. Is this making sense? A little bit? I'll do a couple more examples. You see that? It's kind of a more, tricky way, complex way. But that's basically what we're saying. When we're saying, how do you find all the numbers that go into 12? 1, 2, 4, 3, 6, 12. How do you find all those? Well, they're basically all the things you can make out of 12's building blocks, is primes. Any time the primes get together, they make a number that goes into 12. They make a piece of 12, don't they? They're made out of 12's building blocks. Maybe the 1 is confusing. Let's try another one. What if I started with a number like 20? So let's break down 20. 4 times 5, 2, that's going to be almost the same thing. So it's 2 squared times 5. That's the building blocks, the primes of 20. So if I was to take that 20 and say, okay, I'm going to do the same thing here. I'm going to say you can use no 2s, no 2s, 1 2, or 2 2s. So again, 1 2 is just 2, 2 2s is 4. No 2s is 1. That means I'm using no 2s, meaning I'm just multiplying by 1. I'm not changing the number at all. Is that making more sense? Right, we're multiplying these together. So if you're not using any 2s, then you're just using 1, because 1 goes into every number. And I can use no 3s, which would be the number 1. No, we're doing 3s here. We're doing 5s, huh? No 5s, or 1 5, which would be the number 5. And then just multiply those all together. Every combination thereof. So I'll just take 1 times 1 2 4. That's just going to be 1 2 4. That's just going to be 1 2 4. And then 5 times 1 2 4. 5 times 1 is 5. 5 times 2 is 10. 5 times 4 is 20. There they are. Notice those are all the things that go into 20, aren't they? Is this making sense? Those are all the things the building blocks can make. Now, I'm coming up with a nice formula for you here, but I want you to see it. I want you to see where it comes from. So, thinking about that for a second, what if I had a number? Let's try one more. What if I had a number like 36? What's in the 36? 4 times 9, 2 times 2, 3 times 3. 36 is made out of 2 squared, 3 squared. Any guesses in advance? How many, when I make my box array thing, like how many things are going to be in the box, do you think?
9.
What do you think?
9.
9. Nice. How'd you come up with that?
I think I did 3 across,
3
3 down.
3 across and 3 down. Exactly. How did you know? She's exactly right. How did you know it was going to be 3 across and 3 down? How'd you know that? Diana.
No 2s, 1 2s, 2 2s, and then no 3s.
Yeah.
3s, 2 3s. And then
Exactly.
6 4.
Perfect. She's just looking here and going, okay, the most number of 2s we can have is 2 2s, right? So she's saying, well, therefore, we can have no 2s, 1 2, or 2 2s, right? And then when it comes to 3s, going down the other way, we can have no 3s, 1 3, or 2 3s is 9. Huh? It's all multiplication, by the way. 3 times 3, right? We're not adding anything. It's all multiplication. Yeah, totally. And so then you just fill that in. There's going to be 9, aren't there? So could we come up with a shortcut rule here? What do you got? If I gave you something like, what if I gave you 1 prime to the 3rd power times another prime to the, say, 5th power? How many, when I did the box thing, how many total things are going to be in the box? Is that too quick? Did you see the pattern? What's the box array going to be?
Is it going to be 15?
Almost. Let's go back. Let's look carefully. So you know what math? This is a great time for me to stop and pause for a second and say, why do we study math? This is a great example of why we study math. Are you going to do factors as an important part of your life? No way. No way. Is anybody? I don't know anybody that does factors as an important part of their life. But what we're doing right now is exactly what a scientist does, or what an engineer does, or what an architect does. All right, and which is what? We're looking at patterns and trying to describe the pattern we see. That is math. Math is the science of patterns. It's predicting patterns, describing them, observing them, all that kind of stuff. So right now we're looking and saying, what's the pattern? What's what a scientist does, right? When they look at things in the sky or in the human body, they try to describe the pattern. It's what a lawyer does with the law. You ever think about it? Tons of professions use patterns. That's what you're trying to do in those little minds when you teach them math. It's not so much numbers or moving x's around. Who cares? And most people will never move x's around or numbers. They just use calculator, But they will use patterns. Even a lawyer, right? How do they use patterns? What do they do with the law? All the time they argue based on what? Precedent. That's which is what? A previous law that's like the current one. They look for a pattern in the law of something that happened like this, and it's patterns, isn't it? It's a lot of the thinking. It's not everything, but it's one of the main ways we as human beings think and do things in life. So that's what math is getting at, the ability to handle patterns well. So what's the pattern? What do I do here with the box array? What do these powers have to do with the box array? Do you see the pattern?
You add 1.
Yeah, you take this number and you add 1 to it. Because you always have the option of no 2's, huh? So you end up having a 3, and then same thing, add 1 here, by 3 array. See that pattern? Let's go back to this question now. So if you have some prime to the 3rd times some prime to the 5th, how many total things in the box are there going to be?
24.
Good. Add 1, it's going to be a 4 by 6 array. There's going to be 24 divisors, aren't there? It's going to be a 4 by 6 array. Seeing that? See how that works? Once you've broken it down to primes, now this is only for primes, right? Only when you've broken it down to primes. Those are the building blocks. And, you know, if you have 3 of one kind, then there's going to be 4 different options because you'll have no p's, 1 p, 2 p's, and 3 p's. There'll be 4 different options, etc., etc. You just add 1 to those powers, don't you? So, okay, so what? So what if somebody says to us then, now we're almost there, I want to build a number with 10 divisors, let's say. That seems big, huh? I want to make a number that had, well, let's do it easier. Let's start simple. I want a number that has 4 divisors. I want to make a number that has 4 things in the box. Well, what could I do with a prime p and a prime q? What power and what power? So that it'll end up having 4 things in the box, 4 divisors. That's the number of things in the box, right? What powers do I need there? 1 and 1. 1 for both, huh? Does everybody see that? That's exactly correct. You tracking? Looks like some are, some aren't. Right? Because if those are both 1 power, then remember the rule. Add 1, that'll be 2 times 2, 4 divisors. Won't it? So can I quickly then find a prime that is of that form? What prime, I mean a number of that form? What prime to the first power? What's 1 prime? What's the lowest prime you know? 2 is the lowest, right? You know the primes, right? The lowest prime number is 2. You might wonder about 1. I never talked about 1. 1 is not prime. It's also not composite. As the song goes, 1 is the only lonely number. He's in neither category. 1 is neither prime nor composite. 1, let's just leave it at that. 1 is not prime. I'm tempted to give deeper definitions. 1's not prime. We'll leave it at that. 1's not prime. So anyway, so the lowest prime is 2, 3, 5, 7, 11, 13, etc. So the lowest prime is 2 to the first, times what's the next lowest prime? It's got to be a different prime here. 3 to the first. So 2 to the first times 3 to the first, better known as 6, is got to have 4 divisors. Is that true? Does it? Are there 4 numbers that go into 6? Yeah, 1 times 6, 2 times 3. Those 4 numbers, huh? Do you see the fitting together of facts with primes and facts with divisors? Am I scribbling this all out real quick? Let me give you the rule now. Yeah, you're probably ready for the rule at this point. P to the n times q. Well, here, let's just call it m and n power. Has m plus 1 times n plus 1 divisors. That's the rule we've seen. If you just add, if you have the primes, where p and q are primes, p and q are primes. So do you see the truth of that rule? If you have a couple of primes with powers, if you just add 1 to each of those powers and multiply those, that's times, right? Then that'll be how many divisors? So for example, if I have 2 to the 1 times 3 to the 1, which we know is 6, it has, as we've already said, grab the power, 1 plus 1 times 1 plus 1, meaning 2 times 2, 4 divisors, doesn't it? And we know that's true. There's 6 different numbers that go into 6. 1 times 6, 2 times 3. All right, are we tracking? All right, now we're getting in position to answer the questions. Is that too fast? You guys got to look at that copy down? So that is the important rule right there.
Question.
Yeah, question.
Can 2 times 4 have 6 divisors? 4 divisors?
Yes, really good question. Yeah. So, Diana, right? 2 times 4, yeah. Really good question Diana's asking. Yeah, how about 2 times 4? So how many divisors is that going to have? First power. Add 1, 2 times 2, 4. No, totally wrong. Why? Dana's question is excellent. She's getting right to the heart of the matter. Why doesn't it work for this one? I can't do the rule on this one, huh?
4 is not prime.
4 is not prime. Excellent. Very good. Yeah, this rule will not work for numbers like 4, right? P and Q primes. P and Q must not be reducible. They must be prime. They must be basic building blocks, not things like 4, which is made out of other stuff, right? Good clarification. So remember, it's only primes for which this rule works. So if you have one prime to a power, another prime to the power, just add 1 to both those powers, times those, and you've got the number of divisors that thing's going to have. Because that's how big the array would be to make stuff out of that number's building blocks. Okay, so with that in mind, let's go back to the question. Find the smallest counting number. Well, I scribbled all over that one. Let me do it. Well, I'll just start. This is question 2, part A. Find a number with one divisor. What's a number that only has, we're doing part A here. What number has only one divisor?
1.
There's only one number. Yeah, 1. 1 is the only number that only has one thing going into it. Let's go to part B. What's the smallest number? Now I'll go back to smallest. Smallest number with 2 divisors. Yeah, 2. It's going to be 2, right? Because 1 times 2, 2 things go into 2. Really, we don't even need the rule at this point. They're so easy, we can just guess them. In a minute, we'll start using that rule when they get a little harder. So let's do question C. Smallest number with 3 divisors. What's the smallest number that has 3 things that go into it?
Is it 4?
It is 4. Good job.
1, 2, and 4.
What's that?
Oh,
Yeah, it is 4. But how would we, let's use the rule now. I think we start using the rule to help. But you guys are good job guessing. It is 4. 4 is correct. But how could we do it with like our PQ rule? You know, we had P times Q, you know, and we had some kind of power, you know, 1, 2, whatever. You add 1 to those powers, and you get number of divisors, right? So how could you use that to come up with 3 divisors? How could you times a couple of numbers and get the answer 3? Couldn't we, it's kind of a trick, you're probably not thinking this way. What if we just had a single prime? Only one, instead of 2 primes, just 1 prime, to the second power. How many divisors would that have? Just add 1 to the power. Same rule, just add 1 to the power. So that would have 3 divisors, which is exactly what we're looking for, huh? Right, remember, add 1 to the power. So even if there's just 1 prime, this rule still works perfectly. It doesn't have to be 2 primes. You know that rule I gave you back here? Where I should do, it'll work for 3 primes also. If you have a third prime, PQR to the whatever x, then you just multiply by x plus 1. It works for any number of primes. You know, you just add 1 to all the powers, multiply that together, that's how many divisors. Even if you have only 1 prime, if you just have a single prime, you just add 1 to the power, and that's how many divisors. It works. So coming back here, if I just take that number, 2, and I add 1, it's going to have 3 divisors. That means any number of the form prime, got to be prime, to the second power is going to have 3 divisors, like 2 to the second power or 3 to the second power. Can I do 4 to the second power? No. That's not a prime. So 5 to the second power. All of these numbers, which is what? 4, 9, 25, all of those numbers will have 3 divisors. All of those numbers will have 3 things that go into them, like 4 does, right? What are the things that go into 4? 1 times 4, 2 times 2, but that's only 3 different numbers, huh? So sure enough. So what's the smallest number? You guys are right on. 4 is the smallest number that has only 3 divisors. Getting the idea? Let's go to the higher ones. So 2D asks what's the smallest number that has 4 divisors? Okay, so what's the smallest number that has 4 divisors? Let me give you a second. Yeah. All right, do we have any thoughts? What's the PQ form we need? What powers?
Prime to the P to the first and Q to the first.
Is that going to work? That one's good, huh? Because if we take this power and you take the power right here and you add 1 to it, and you take the other power and you add 1 to it, 2 times 2, 4 got to have 4 divisors, right? So any prime to the first times other prime to the first. So that would be like in anything. So that would be like 2 to the first times 3 to the first, which is 6. Or 3 to the first times 5 to the first, which is 15. or 5 to the first times 7 to the first, which is 35. All those numbers will have 4 divisors. Is that true? What goes into 6? 1 times 6, 2 times 3. What goes into 15? 1 times 15, 3 times 5, etc., etc. They all have 4 divisors, don't they? So anything of the form prime to the first, prime to the first. But there's another form.
Is it p to the third?
Yeah, good. Any prime, just a single prime, not 2 primes, any single prime to the third power, right? Add 1 to that power. It's got to have 4 divisors, isn't it? That means any prime to the third power will also have 4 divisors. There's 2 different forms or models or templates that'll lead to numbers with 4 divisors. You can have prime to the first, or just 1 prime to the third by the adding 1 to the power rule, right? So what's an example of that? What's a prime to the third? 2 to the third, which is 8, or 3 to the third, which is 27. Does 2 to the third, 8, does 8 really have 4 divisors? What goes in 8? 1 times 8, 2 times 4, yeah. 27 is the same way. 1 times 27, 3 times 9, yep. All right, so who's the overall winner then? What's the overall smallest number with 4 divisors? 6. So the answer is 6. That's the smallest number with 4 divisors. Is that making sense? We're going to go to bigger ones. It's going to get a little harder. Getting the idea?
Yeah.
All right. So let me give you a hint as to how you knew you could discover there were going to be 2 different models there, because sometimes you'll really need them both. This time it probably didn't matter. Probably if you just found this, you found the 6 right away, and 8 doesn't matter. But other times it will. So let me give you a hint. There's 2 ways to multiply to get 4, aren't there? 1 times 4 and 2 times 2. Right? And that's what leads to these models, right? What is this? 2 times 2, that model. What is this one? Just 4, the other model. Making sense? So if there's more than one way to multiply to get the number, there's more than one model to make it happen. All right, let's go to E. Probably using up all of our time on this one problem. How about 5 divisors? What's the smallest number with 5 divisors? Give you a second. How many ways are there to multiply to get 5? There's just one way. 1 times 5, huh? So there's only going to be one model here. There's only one model. And what is it? P to the 4th. It's got to be P to the 4th, right? Add 1 to the power. Any prime to the 4th power. So what's the smallest prime to the 4th power? 2 to the 4th, 16, done. 16's got to be the smallest number with 5 divisors, does it? 1 times 16, 2 times 8, 4 times 4, 1, 2, 3, 4, 5 divisors. This making sense? This, by the way, would be very helpful in that locker problem of the week, where they walk through with the lockers. It's connected to all this kind of stuff, if you want to solve that one. All right, we good? Shall we go on? No, we're going to get to bigger ones. They're going to get harder. 6 divisors. Find the smallest number with 6 divisors. Let me give you. Right, so that would be prime to the prime to the first. Because you add 1, 2 times 3 is 6, right? Or what's the other model? Any prime to the 5th. Add 1, 6. So, right? You tracking with me? And so we did this one. So this would be. So yeah, what's the smallest thing you can make with that model? Yeah, try that. No, there is a little bit more to think about here. Yeah, chalk that out and realize that. So in other words, I could. You tell me. Somebody want to tell me? What's the small way and the big way to do even just this one model?
You can do 3 to the first times 2 to the second, which is the small way, and then the big way to do that one is 2 to the first times 3 to the second.
Everybody see that difference? See, you're going to use the 2 and the 3, of course. They're the 2 smallest primes. But there's 2 ways to do that. The better way is to put the smaller prime to the bigger power. That'll make the overall smallest number. We're trying to make the smallest, right? That'll be 12, right? 3 times 4. This will be 18. This one, what's the smallest thing this model can make?
32.
Yeah, 2 to the 5th, 32. Is that good? Does that make sense on that? Cameron, I'm going to have to, you're too good. I'm going to have to make other people answer. Good. I had a few of you as well. Good, that's really good. Is everybody with Cameron on that? She's definitely got it. Do you all got it?
Yeah.
Is that making sense? Is that good? So 12, so the winner is 12, I think we said that earlier, did we, half an hour ago or whatever. 12 is the smallest number. Is that good? All right, we don't want to use, we've only got 10 minutes left. I'm going to use all of our time on this. Maybe I better just jump. So what's the big, 10? Is 10 the biggest one on that sheet?
Yeah.
Is that it? Okay, so let me just jump there. What's that? At G-H-I-J? It's J. So let's just jump to 10. Oh, no, 8's tricky. Let's jump to 8 divisors. G-H, H, 8 divisors. Find the smallest number with 8 divisors. Okay, so what's the P and Q models?
P to the 7th?
Yeah, good one. P to the 7th. That's certainly going to have 8 divisors, right? The add 1 to the power rule. So, and what's the other one?
P1 times P3.
Yeah, good. Because add 1, that's 2 times 4, going to have 8. Everybody good? So there's that model, there's that model. Right? Either one of those models will produce numbers that has 8 divisors by the add 1 to the power multiply rule, right? Add 1, 2, add 1, 4, 2 times 4, 8, and just add 1, 8, right? We good there?
Yeah.
So now let's stick in the smallest primes we possibly can to make the smallest possible number. So if I'm going to put in, you're always going to be using 2 and 3. Those are the smallest primes, right? So 2 and 3, but which way do I do it to make that thing crank the smallest number out?
Through the first and to the...
Yeah, you put the small number to the big power, huh? Like that. So what's that, 324?
Yeah.
Okay, and what about this one? Just 2 to the 7th. Isn't that a big number? 128? 128. So there we go. Does that make sense? Is there another model? Did anybody find another model to produce numbers that have 8 divisors? Anybody produce a model with 3 letters, 3 primes?
I have a question.
Yeah.
Would you only use like P to like 1 or P to 2 like when it's odd numbers? Like when you're trying to figure out like the following like odd number? Because like when you do it for 6, like you get.
Oh yeah, like when we do 7 divisors, you mean?
Yeah.
Yeah. Let me answer that in just a second. Let me finish up, and then I'll do that one real quick. You're right. You would only do the one model, but I'll explain. Yeah, more. Yeah. How about one more thing before we move on from this one? How about with 3 letters? Is there any way to make 8 things out of 3 numbers multiplied? What 3 numbers can what times what is 8?
2.
2 times 2 times 2. So what is the powers? 1, 1, 1. Right. Add 1, add 1, add 1. 2 times 2 times 2. 8. That model's got to also produce numbers with 8 divisors, doesn't it? So what's the smallest thing that model can crank out? 2 to the first, 3 to the first. Now you got to do a different prime. You can't repeat. 5 to the first. So that's actually going to be 30, which is not smaller. So the winner is 24, but you got to watch out. Sometimes there's other models on that. That makes sense? So sometimes there's other models. All right. Yeah, good question. Now for the one right before, what was it, G? That I skipped. Yeah, when they're odd, Diana was mentioning, what about when they're odd, like 7 divisors? What's the deal when they're odd? There's only one way to do them, huh? They'd just be P to the 6th. There's no other way to make the number 7. How else can you multiply to be 7? Oh, that's not true. That's not true for all odd numbers, is it? I'm wrong. GH, like if you did I, which is 9 divisors. Yeah, so what I should say is any number that has only one way to multiply it. There's only one way to get 7. Just 6 add 1. But there's other ways to get 9. You could do P to the 8th, or what's the other way to get 9? What times what is 9? 3 times 3. So what am I going to do for the P and Q powers? 2 and 2. That would also make 9, huh? So you'd have to test both of those. Yeah, so actually, there we go. By the way, notice how I don't walk, even there, I said the wrong thing and then corrected it. I just want to continue to show you, math is not about memorizing. I'm just showing you, look, I don't know it, do I? I don't walk in with my head full of all the facts. Well, that's one line. Who cares? I mean, it's dumb to have these things memorized. But math is about discovering and logic. That's what you want to do for kids when you teach them. All right, I'm going to run out of time completely. All right, find the smallest counting number. It's the smallest number that is divisible by all the numbers 2 through 8. All the numbers 2 through 8. So that means 2 through. Let's do part A here. Forget about part B right now. 2, 3, 4, 5, 6, 7, 8. I want to make a number that all those numbers divide evenly, like a big number, like, like, I don't know, 100 or something, I don't know, I'm just guessing around. Some big old number that all of those go into evenly. Divide evenly into. Does that make sense, the question? First off. And I want it to be the smallest. Because there's probably a lot of numbers that all those numbers go into. Really, if it didn't say smallest, you could just multiply those all together in your calculator. That's for sure a number that they all go into, but it's not the smallest. So the trick is to build the smallest thing that they all fit into. Get the idea? I want to make the smallest thing that all these could go into perfectly. How are we going to do that? The answer to all these difficult questions is always primes, isn't it? Because those are the building blocks. Those are what make all the numbers. So if we think about primes, 2 already is prime, 3 already is prime, but 4, he's made out of 2 2s. 5 already is prime. 6 is made out of 2 times 3. 7 already is prime. 8 is made out of 3 2s, isn't he? So if this new number that I'm building has to be made out of that stuff, but I want to do it minimalistically. I want to make the smallest thing that contains all those pieces. Do you get the idea? So let's do it. I need to have some 2s. How many 2s do I need to have? Well, you don't need all the numbers to go in at once. You just need them to be in there one at a time. So we need at least 1 2. We need at least 2 2s. We need at least 3 2s. You need 2 to the third. Does that make sense? I'm trying to build the smallest thing that these 8 will go into that number now. Because that's an 8, isn't it? You tracking with me? That is 8. 2 times 2 is 4 times 2 is 8. That's 8. So this number I'm building, 8 will divide into it, 2 will divide into it, 4 will divide into it, because it's got an 8. It's got the most number of 2s that anybody has, so it can accept any of their 2s. Let's go on to 3s. What's the most number of 3s that anybody has? Just 1. He's got 1, he's got 1, that's it, just 3 to the first. What's another prime they've got to have? 5. What's the most number of 5s anybody has? Just 1, just this guy. What's the next prime? 7? Just one of those, and that's it. Right? If those primes, whatever that multiplies out to be, those primes, all those numbers can go into it. See what I'm talking about? All these numbers can divide into this because he's got their pieces. He's made out of their pieces. Just enough. Nothing extra. What is that number, by the way? 840? Thank you. 840. That would have been crazy to try to come up with, even with a calculator, by guessing, right? See how quickly primes get to the issue. All right.